José Alejandro Samper.
Mariana Lave.
Juan Camilo.
Andrea Rincón.
Listo. Listo. Yo. Como raro dictar clase en inglés en Colombia, pero bueno, me toca. Pero obviamente, si tienen alguna pregunta, yo también hablo español, entonces no tienen que preguntarme en inglés ni nada. Y pues, bueno, ustedes han visto la clase acá, yo le daba ya, pero entonces hay cosas que de pronto si no están claras me paran, lo que sea, me avisen y hablamos. Ok, yes. No, hermano, esto me parece muy raro. So, we were talking about the exchange property and the deletion property, two very important properties of Coxeter groups. So we said if you have a Coxeter group, a Coxeter system like this, then that has two properties, which are, I'll remind you, exchange property, and that says that if you have some element of the group, which you write in terms of generators in any way as S1 up to Sk, and then if you have some generator, little s, such that when you multiply W by S on the left, it becomes a shorter word. Then, is that, first of all, it tells you that if you multiply SW, you could write it as S, S1, S2, up to Sk, but it tells you that's wasteful because this word is shorter, and that means that you can get rid of the S and just get rid of one of these guys. Okay, so S1, then Si is missing, up to Sk. This is called the exchange property, and we proved that it's true. Then we proved another property called the deletion property, which says that if you have some element of the Coxeter group, which you have written in terms of generators as S1 up to Sk, and if this is too long, if this is not a reduced expression, then you can reduce it by eliminating two of the Si's. Okay. This is for some I, and this is for some I and J. Okay. And I said very briefly at the end of last time that if you did not like this signed permutation representation very much, then this is good news for you because these were the two main things that we wanted to get out of that signed permutation representation. And we will not need it so much anymore, but we will need these two things very often. So if you have any questions about them, please tell me. Very important that you understand what they say. Okay? Any questions about them? Okay. So last time I stated a very important theorem of Matsumoto, which says that if you have some group, any group, and you have a set of generators of order 2, then the following properties are equivalent. The first property is that these guys form a Coxeter system The second property is that they satisfy exchange. And the third property is that they satisfy deletion. Maybe we should invent some names for these things in Spanish, because you'll have to use them very often. So I don't know if these words exist in Spanish. I don't know that a lot has been written in Spanish about Coxeter groups. So I guess we should call exchange intercambio, deletion, eliminación. Okay. So let's call them that way, and if you ever need them, that'll be the name. Exchange, intercambio, deletion, eliminación. Okay. So my main goal for today is to prove this theorem for you. But before I prove it for you, I want you to understand that this is an amazing theorem, because I think in the homework you realize that proving that something is a Coxeter group is difficult. It's not easy. And this gives you a much, in some cases, a much easier way of proving that something is a Coxeter group. You just prove that it satisfies the exchange property or the deletion property. Okay. So let's see. So we proved some of these things already. For example, we proved that Coxeter systems have the exchange property. So this is proof. We proved this already. We proved that Coxeter systems satisfy the deletion property. And if you look carefully at how we did it by proving that exchange implied deletion. So just look at that proof carefully, and you'll see that we never used that W was a Coxeter group. We used that W satisfied exchange, and we proved deletion. So these two things we proved already. Okay? And so now let's go in the other direction. So let's prove that deletion satisfies exchange. Deletion implies exchange. Okay? So suppose that we have a W and S that are not necessarily a Coxeter group, but they have the deletion property. And let's prove that these guys have the exchange property. So then we take W equals S1 up to Sk, and we take S such that L of SW is less than L of S1 up to Sk. And we have to prove that conclusion over there. Okay. Now, how do we prove it? We prove it in the following way. The thing is, we know that the length of this word is not k plus 1. I mean, we know that this word is not reduced because this one has length at least k, so this one has length less than k. So this is not a reduced word. Right? So if it's not reduced, then we know that by the deletion property we can shorten it. And we can shorten it by getting rid of two of them. Okay? Now, there's two cases. Either we get rid of S and some Si, or we get rid of Si and Sj. So let's do those two cases. Either we got rid of Si and Sj, or we got rid of S and some other guy. Okay? Now, can you tell me which one of these two is the case? I think one of them cannot be. This one cannot be, because then you can cancel the S's and get a shorter expression for S1 up to Sk. And so that means that really what we have is SW equals exactly what we need it to be. It's exactly what we have to show. Okay. So that's the proof. There isn't very much to do here. Any questions about it? Okay. So this is no, this is what happens. Okay. Now, as you can imagine, the difficult direction of this theorem is the one that we haven't proved, which is that either one of these two properties implies that we have a Coxeter system. So that's the last thing we will do. And by now we have proved that 2 and 3 are equivalent. So we're going to assume that both of them happen, and then we're going to prove 1. Okay. So suppose that 2 and 3 occur, and let's prove 1. So if you have deletion and if you have exchange, then you have a Coxeter system. Okay. Now, before I do this, I want to talk a little bit about what's the difficulty here. How do you prove that something is a Coxeter system? Because I think that has been the biggest confusion in this class so far for people, and the most difficult thing to prove in the homework. How do you prove that something is a Coxeter group? Let me show you how you don't prove that something is a Coxeter group. Let me show you how you do it wrong. So let's open a parenthesis here. How not to prove that something is a Coxeter group. And actually, what I'm going to explain now, I'm basing from a very good idea that someone posted on the forum, and it was one of you, but I forget who. It was about how not to prove that S3 is a Coxeter group. Okay? So, wrong proof that S3 is a Coxeter group. Well, we're going to do this. Let's say that, so what do you need to have a Coxeter group? You need to find generators that satisfy the correct relations, right? So generators. Well, we know that the transpositions generate the symmetric group. Okay, we know that. In fact, you know already that these two guys generate everything. But I'm going to ask you to forget that for now. And let's say, well, these guys are generators. Okay? They definitely generate the group. Let's call them A, B, and C. And what relations do they satisfy? Well, each one is a transposition, so if you square it, you get the identity. And we've done this computation several times, that if you take 1, 2, and 2, 3, then ACA equals CAC. Or in other words, AC cubed is the identity, and in exactly the same way, you're going to find that BC cubed is the identity and AB cubed is the identity. Okay? And then you might be inclined to say that's it. S3 is a Coxeter group with generators A, B, and C, and these are the Coxeter relations. Okay? That's my proof. Why is this an incorrect proof? It's a subtle but a very important thing. What I supposedly proved here is that S3 is the Coxeter group for this Coxeter diagram. Right? A 3 here, a 3 here, a 3 here. But what's the issue here? The issue here is that what is this group? Let's call this group W. Okay? Well, W Let me actually just change the names here so that we don't get confused with the notation. So W is generated by A, B, and C. It satisfies the same relations. Okay? And supposedly, what I proved is that S3 and W are the same thing. But in fact, I have not proved that, and the reason is that I proved that S3 satisfies all the relations that W satisfies, but I did not prove that S3 does not satisfy relations that W does not satisfy. Okay? And in fact, S3 and W are not isomorphic groups. The reason being that, actually, we proved last time that there are no relations between the generators of a Coxeter group. So in W, there's no relation between A, B, and C. But in S3, there is such a relation, right? We know that. We know that B can be written as ACA. Or as CAC if you want. So that means that BACA is the identity. Okay? And here you have a relation that is satisfied in S3 and is not satisfied in W. And this is why these two guys are not the same group, and why this is not a proof that S3 is a Coxeter group. My mistake was choosing too many generators. Okay? I forget who said this. Someone explained this very nicely in the forum, and I'm just repeating what they said. So how do you prove that something is a Coxeter group? Well, you have to check three things. First of all, that you have generators that generate. Then that you have every relation that you're supposed to have. But then you also have to prove that you don't have any relations that you're not supposed to have. Okay? No other relations like something like this. Okay? So that's what we're going to do. By the way, let me state a problem from the next homework that is nice. S3, we proved, is the symmetries of an equilateral triangle, because we proved that S3 was the same as D3, the dihedral group. And this group over here, the exercise is to prove that this is similar, but it's not the same thing. This group is actually describing the symmetries of not a single triangle, but a triangular grid. Okay. An infinite triangular grid. So if you compute the group of symmetries, there are some things that leave this alone, right? For example, if you rotate this by 60 degrees, by 120 degrees, you get the same thing. So that's one symmetry of the triangular grid. So the homework will be to show that actually the symmetries of this guy are exactly described by this group that is not S3. Okay. It's a nice exercise. Okay. So any questions about how not to prove that something is a Coxeter group? Is that clear? So let's now prove this last thing then. Deletion and exchange imply Coxeter system. Okay. So we have W, we have S. What's the first thing that we need to build a Coxeter system? Remember, we need two things, right? We need, first of all, the generators, and we know those. And then we need the relations, and we don't know those yet, actually. Because the way I'm describing this to you, W is some group that you know nothing about, except that it satisfies these properties that don't look at all like Coxeter properties. So we have to build a matrix somehow if we want to say that this is a Coxeter system. And the way we're going to do it is exactly by doing this thing that we did here. If you wanted to build a matrix out of A, B, and C, you would just find the order of AC, find the order of BC, find the order of AB, and those would be the numbers that you would stick up here. And so we're going to build a matrix by saying that this is just the order that this thing is supposed to have. Okay? It's the only reasonable choice for this number. You just look for your element, your generator S, look for your generator S prime, you multiply them together, and you see what order that thing has in your group. You check, is S prime the identity? Is it square the identity? Is the cube the identity? Until you find the first power where it's the identity, and that's going to be the M. Just like here, it was 3 that we wanted to have. Okay? So this is going to be our M. And then we claim that W is the Coxeter group for generators S and matrix M. Okay? And to prove that, we need to do 3 things. As I just told you, the first thing is to actually check that S really generates W. Why does S generate W? Just by definition, right? Because I said S is a set of generators for W. So that's one of the conditions that I have. So the question is, why is M finite? And the answer is that it isn't necessarily. So sometimes you will find that no power of SS prime is the identity, and then this number will be infinite, which we know sometimes we have to do in Coxeter groups. It's a very good point. So infinite, if the order is infinite. I guess I'm not really saying anything here. But that's a very good point. We are going to, in general, get infinities here in this matrix. Okay? So the first thing is that S generates W, and that's true. The second thing is that W satisfies the correct Coxeter relations. Coxeter relations. But again, what do I have to check? Well, I have to check that if I multiply S prime, and I raise that to the power M of S comma S prime, I get the identity, and that is free also by the construction. You see, this is exactly the reason why I chose M to be what it is. Okay? And so the tricky thing, as it was the tricky thing in every homework problem, is how do you make sure that this is enough? So that's the third and key step, which is that W has no other relations. In other words, every other relation something S1, S2, Sk equals the identity. Whenever you have a relation in your group W like this, then the only reason that relation holds is because it's a combination of the Coxeter relations. Every other relation is a consequence of the Coxeter relations. Okay. So this tells you the only way of building true relations in this group W is by saying maybe you take one Coxeter relation, then multiply by another Coxeter relation, then multiply by A inverse maybe. The only relations are consequences of Coxeter relations. Okay? That's what I have to prove. That's what I'm going to prove. Okay. So this is exactly what I want to make sure doesn't happen. That I have a relation like BA, CA, which cannot be obtained as a consequence of these 6 relations. This is what I want to make sure doesn't happen. Okay? So let's just take some relation and prove that it's a consequence of the Coxeter relations. So let's induct on K. But maybe the first thing that you should notice is, I don't know, what can you tell me about K? It's even, right? It's even because this guy has, we know that elements of a Coxeter group are either even or odd. And this one has an even expression of length 0, so any other expression has to be even as well. So let's just call this 2K and induct on K. Let me actually just rewrite, it's going to be a little bit easier if I rewrite this equation by leaving K guys here and sending the other K guys to the other side. We write as S1 up to Sk equals S1 prime up to Sk prime. Okay? Uh-huh.
In every group you have even or odd elements?
In every Coxeter group, not in every group, but this is something that we proved that if you have a Coxeter group W and a set of generators S, then if you want to express an element of W in terms of the generators, the parity of the length of that is always either always even or always odd. And remember, I told you that the even guys form something called the alternating group.
Yeah, but we're showing that this is a Coxeter system. So why can we assume this is a Coxeter?
You're absolutely right. Thank you. I'm lying to you. Why? Prove to me that this is even. You cannot use that this is a Coxeter group. You're absolutely right. So how can I prove that this is even? There's a different reason for that. What can we prove? I mean, what can we use? Yeah. We can only use either exchange or deletion. These are the only things we know about this group. So how do we prove it? The thing is, look at what deletion says. If you have a word that is not reduced, then you can take 2 guys off. So here you have so the correct proof is, here you have something of length 2K, which is not reduced. That means you can take 2 guys off. It's not reduced. Take 2 guys off. It's not reduced. 2 guys off. It's not reduced. Finally, when it's reduced, it has to be the empty word, because that's the only word of length 0. And you took 2 guys off at a time. So that means that this is even. That's the correct proof. Thank you. So this is even, and I rewrite it in this way. Okay. So what can I do now? I have to use deletion and exchange. That's the only thing that I have. Okay? So let's do something. Let me multiply. Actually, let me do 2 cases. So case 1 is that this is actually reduced. No, not reduced. Okay? So either this has length k or it has other length. First, let's assume that it's not reduced. Okay. S1 up to Sk is not reduced. So now, that means that I can take the max I for which Si up to Sk is not reduced. Okay? I know that for I equals 1 this is true, and so I'm just going to look for the biggest I that satisfies that Si up to Sk is not reduced. And what I'm going to accomplish there is that Si plus 1 up to Sk, I plus 1 is bigger, so this is reduced. Okay? And let me rewrite this as like this. Okay? Any questions about what I'm doing here? this thing is reduced. So that means that the length is k minus I. This thing is not reduced. Okay? So what can you tell me about its length? Well, you have to remember a lemma that I proved for Coxeter groups that says if you take something of length k and you multiply it by a generator, then the length is going to become k plus 1 or k minus 1. That's another homework problem, by the way. You can start thinking about it. So if this thing has length equal to this, then this thing has length that plus 1 or that minus 1. Now we proved it for Coxeter groups, but in exactly the same way that you pointed out, we can prove the same statement just assuming deletion. Okay. So this thing has length k minus I plus 1 or k minus I minus 1. But we know that it's not k minus I plus 1 because then that would be reduced. Because this thing has length k minus I plus 1. If this is not a reduced word, that means that the element has to have length k minus I minus 1. Okay? The point being that I have an element of the group that became shorter when I multiply it by Si. Okay? And this is exactly the kind of thing that I want to happen because that's when I can apply my exchange lemma. My exchange lemma says, if this is true, then it must be the case that Si plus 1 up to Sk can be written by just getting rid of one of these guys. Okay? Any questions about that so far? Okay. So now, let me multiply by S1 up to Si minus 1. So what I get on the left-hand side is just W. What I get on the right-hand side is W, except that I remove I and I remove J. Okay? So this equation is true. Now, how long is this equation? This equation had length 2k. This equation has length k plus k minus 2. It's a shorter equation. This is shorter. It's shorter, so that means that by the induction hypothesis, this is a consequence of the Coxeter relations. Okay? So I can start with the Coxeter relations and in some funny way get to this equation and then get to here and get to here and prove my relation that I want to prove. Now let me say it a little bit differently. This is a shorter equation, so it is a consequence of the Coxeter relations. Okay? So we agree so far. This is a shorter equation, and that means that it's a combination of the Coxeter relations. Now, there's another equation that is true, which is that this is equal to S1 prime up to Sk prime. By assumption, these guys are equal. What's the equation that I'm trying to prove is a consequence of the Coxeter relations? I'm trying to prove that this equal to this is a product of Coxeter relations. Now, I know that this equal to this is a product of Coxeter relations. What about this equal to this? You see, this is also an equality in the Coxeter group. And the equality that this is equal to this also has length 2k minus 2. So that means that that is a consequence of the Coxeter relations. Yeah. And so how would I prove that this is a consequence of the Coxeter relations? Well, I basically first prove that this equals this by multiplying Coxeter relations together. And then I prove that this is equal to this by multiplying Coxeter relations together. And what I'm going to get as a consequence is that the equation that I wanted to prove is not just true, but it's a product of Coxeter relations. Okay. Any questions about it? It's a subtle argument. It feels like we did nothing and we proved something. You should think about it carefully, make sure you understand it, but that's the argument. Okay. Any questions about it? Case 2 is that this is reduced. Okay. So what does that mean? Let's look at this. Now, what happens if, and again, I know this equation is true, and what I want to prove is that it's a product of Coxeter relations. How do I do that? Well, what happens if this guy and this guy are equal to each other? If this guy and this guy are equal to each other, then you cover them, you get a shorter relation. Because that relation is shorter, you can prove it using the Coxeter relations, and then just multiply by this guy on the left. So if these two guys are equal to each other, there's nothing to prove. So suppose S1 is not S1 prime. Okay? Now what I'm going to do is multiply by S1 prime. What length does this have? We know that this guy had length k. And so this is going to be either length k plus 1 or length k minus 1. So which one is it? So k minus 1, why? You can't tell if you multiply here, but you can tell if you multiply here. If you multiply by S1 prime, you're just going to cover something up and get a word of length k minus 1. Okay. And that means that this is smaller than the length of S1 up to Sk. And again, this is exactly the kind of thing that we want, because we want something that when we multiply it by a generator, we get something shorter. Then we can apply exchange. Exchange tells us what does it tell us? It tells us that multiplying by S1 prime is the same thing as taking out one of the S's here. Okay. Let me rewrite this as S1 up to Sk is equal to S1 prime, S1 dot dot dot, Si dot dot dot, Sk. Okay. What am I going to do now? I'm going to pull off a similar trick as the one that I did just now. I'm going to say this guy is equal to this guy by assumption. Okay. Let me call this 1, 2, 3. Okay? Now, what I want to show is that 1 equals 2 is a consequence of Coxeter relations. And the way I'm going to do it is by proving 1 equals 3 is a consequence, 2 equals 3 is a consequence. So let's look at 1 equals 3. Okay, forget about 2. How do I prove that 1 is equal to 3? Well, you see, the thing is, the way you prove it is by proving that this is equal to this, but they start with the same guy. So to prove them, you would have to prove that this is equal to this. Yeah, I just canceled the S1 prime and the S1 prime. How do I prove this? Well, again, it's shorter because this has length k minus 1, this has length k minus 1. It's shorter, and so it's a consequence of the Coxeter relations. Okay. So I can prove that 1 is equal to 3 using Coxeter relations. What remains is to prove that 2 is equal to 3. Okay. Let's go over here. So now let's prove that 2 is equal to 3 is a consequence of Coxeter relations. Well, what we have to do is just hope that this is a shorter thing also. So 2 equals 3 says S1 dot 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 up to Sk equals S1 prime S1 dot 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 Si dot 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 Sk. Is this shorter? The way I have written it, this has k terms, this has k terms. But I can shorten it, right? I can shorten it because these guys are the last ones that appear here. Yeah? So if I can, I mean, this is equivalent to saying S1 up to S, where should I stop? I, right? Because I'm getting rid of Si plus 1 up to Sk, so I should stop at I. This is equal to S prime, S1 prime, S1 up to Si minus 1. And that's a shorter relation. This has length I, this has length I. It's shorter, so I prove it using Coxeter relations. And then I just multiply by the same thing on the right on both sides. Okay. Are we sure? I'm lying to you. Why am I lying to you? I'm not really lying to you, but I'm hiding something from you. This is length I. Yeah? I'm saying that's shorter, but what's I? Where did I appear in the first place? I appears here the first time. Is I smaller than k? Almost always. I is between 1 and k. So if I is anything except for k, we're fine. But if I is k, this is not a proof. So let's say, okay, if I is less than k, that means that this is a consequence of Coxeter relations. And that means I proved 1 equal to 3 using Coxeter relations, I proved 2 equals 3 equals using Coxeter relations, and then I'm done. That means I'm done unless I is less than or equal to k. And I still have some work to do. So, we're done unless we have something like this. We're wondering whether we can prove something like this. We have an equation like this, yeah? And we're wondering if it's a consequence. Okay? And we just proved that either the proof is finished or it's reduced to proving this is equal to this as a consequence of Coxeter relations. So either we managed to prove this, or we reduced it to proving this, which is of the same length. That's what we have so far. We're going to have to work a little bit harder. You shouldn't expect an easy proof. It's a good theorem. So we're going to have to work a little bit harder, but actually we're almost finished. You should be a little bit suspicious of this proof so far, because where have I used Coxeter relations? I mean, I'm doing this induction, right? But this is some self-referential thing where I haven't written a Coxeter relation yet, so how could this be a proof if I haven't used any Coxeter relations? So we should be a little bit suspicious. And I'll show you now how we're going to come up with Coxeter relations. We're trying to prove this. Okay, let me just rewrite this. And we're wondering, is it a consequence or not? Okay? And we prove that either we're finished or we reduced it to the following thing. Let me write it in this way. What's the best way to do it? First, let me send the S1 prime to this side. And then let me just write this on the left-hand side. So I'm saying either I prove this or I reduced it to proving this. This is the same length, but I can make the same argument again. Okay? And hope that this time with this word and this word, hopefully it'll work. So we do the same thing. Okay, we say, okay, whatever it is that I just did and I just erased, try it again with this one and this one. And either that will work or it will be reduced to something different. So, okay, or reduce to this. Now, to prove this one, I'm okay, or I reduce to the same thing, but now corresponding to this word. So how do I get the thing corresponding to this word? Well, what I do is I take this word and put it here. So this one now takes the place of this one. And for the word on the left, what I did is that I took the last letter of this one and put the first letter of this one. So what I should do is take off the last letter of this one and put in the first letter of this one. Okay. So I'm saying if you make the exact same argument that I just made, but for now this is equal to this, either you're going to succeed or you're going to reduce it to this other problem, this is equal to this. But this is starting to look a little bit better, because this is starting to look like a Coxeter thing. Okay? Repeat. We would like to know, is this okay or should we continue? Well, either I make the same argument and either I succeed or I get the same thing, except again, what I do is I take the left word and put it on the right, so the left word now becomes S1, S1 prime, S1, S2, up to SK minus 1, equals.
One question. On the third line, shouldn't you have S sub k, not S sub k to 1, or? S sub k. Because the length doesn't correspond.
Oh, here.
Yeah.
K minus 2, you're right. It should be K minus 2 because I said to go from here to here, I get rid of the last one and put in the first one. So I should get rid of the last one as K minus 1 and put in the first one. So this should be a K minus 2. Another way of saying that is that I should have K things here. And I have 1, 2, and then K minus 2. So this is also a K minus 2. And then I make the same thing, okay? This is getting kind of boring, but it'll be over soon. So again, we take off the last word, the last letter, and we put in this first one. And you see the pattern, okay? So you repeat. Either we succeed or we try again, succeed or we try again. What are we going to get when we keep repeating? What we're going to get is S1 prime, S1, S1 prime, S1, until everything else has disappeared, equals S1, S1 prime, S1, S1 prime, etc. Okay? And if a relation like this is true, it's because this is the Coxeter relation. If this is true, it's clearly a consequence of the Coxeter relation. So, a consequence, finally. And then once I manage to get this, then I say, okay, then if this is a consequence, then this is a consequence, this is a consequence, and I get back to the top. This doesn't go to infinity because this word has length k, and you see what's happening is each time you have k guys, then it becomes k minus 1 guys, then it becomes k minus 2 guys, and so on. And eventually they're going to all disappear. Okay? And in particular, what that's going to mean is that when you make this argument, this S1 prime S1 is never going to have order infinite. Because you just proved a finite relation for it of length k. No, yeah, I mean, I started with this relation, and then I proved a bunch of other relations that hold in my group W. So I proved that this relation holds in my group W. And if this is a finite relation, that means that the M corresponding to S1 prime and S1 for W is finite. Okay? So this is the proof. Okay? It's a little bit of a tour de force. But you should expect it. When you want to use a hard theorem, you should expect a hard proof. Okay? So now we have Matsumoto's theorem available to us. Okay? Let me say very, very quickly an application. For example, how do you now application, how do you prove that the symmetric group is a Coxeter group? I think you agree this was hard. This was hard, but now it's easy. Because now you say, let's prove that we have, I don't know, you choose, what do you prefer? They're both equally easy. Let's say deletion. I mean, they're both equally easy. Deletion. Let's say that you have a W equals S1 up to SK, and the length of W is not K. It's smaller. How should we see an equation like this in the symmetric group? Well, we know that it's just this wiring diagram, right? So cross, something like this. Okay. Is that reduced? I think it's reduced. Let's do something to break it. Is that reduced now? I think that shouldn't be. I'm going to keep doing this until I get something.
You already have it.
I think I had it already, but just to be very sure. This is not reduced. Why is this not reduced?
You can cancel the second one.
The second one? From here or from here?
Oh.
This one?
Top to bottom.
And?
3,
I think. No,
1.
yes.
I can cancel these two. Why? Because this is a crossing of 1 and 3, and this is a crossing of 1 and 3. How do we know if something is not reduced in the symmetric group? When you draw the wiring diagram, if you crossed wires twice, you're not reduced. If you didn't cross wires twice, you're reduced. So, how do you prove deletion? Take a word that's not reduced, you cross 2 wires twice, uncross them. Yeah? That means I'm just removing this generator, and making a shorter word. Okay? So that's the proof. Now, this should explain to you why this was a hard problem, because if you didn't know this, you basically had to prove something like what I just did. I mean, this is really the computation that we did, in particular for the symmetric group. Yeah? And this is why you should be very grateful from now on that this is a very powerful tool that we can use. Okay. Let's stop there. Any questions? Creo que paremos el video y si tienen preguntas, me dicen.